Hello everyone, my name is Zekeriya. I am a PhD student in the Jusdl University in the Department of Electrical and Electronics Engineering. I am from Izmir, Turkey. The talk is about Jusdl, Julia-based system description language. We will first start with the features of the package. The first feature is the simulation of a large class of systems, and these systems can be static systems and dynamical systems. Dynamical systems can further be divided into two as dynamical systems with differential equations and dynamical systems with differential equations. Here you can see the type of differential equations that can be solved in Jusdl, and Jusdl uses differential equations package to solve these differential equation types. The next feature of Jusdl is the simulation of models that have components represented by different equation types. In Jusdl, a model may have a component that is represented by ordinary differential equation and may have another component that is represented by, say, stochastic differential equation. And we just construct those components individually and connect them together, and the model is ready for simulation. So there is no need to construct a unique mathematical equation to represent the whole model. We just construct the components individually. Online data analysis is possible, and especially with the user-defined plugins, the scope of online data analysis can be enriched by the users. The users also have the flexibility to enlarge the component library by defining their own component types. For example, users may define their own source types, their own system types, etc. Okay, before going on with the details of the package, let's have a first look at the package. On the left, we have a simple model consisting of 4 components and a couple of connections. Connections are represented by arrows, and components are represented by rectangles here. And in addition to the components and connections, and the model also has a reference time clock. And this is the block diagram of the model, and there is a strong relation between the block diagram and signal flow diagram of a model, and each component in the block diagram of a model can be associated with a node in the signal flow diagram. Similarly, each connection in the block diagram of a model can be associated with a branch in the signal flow diagram. So by adding new nodes to our model, we are actually adding new components to the model, and by adding new branches to the model, we are actually adding new connections to the model. Okay, let's construct this model in Jusdl. We use a def model macro for that purpose and specify the name of the model. Then between begin and blocks, we specify the nodes and branches. For example, this expression means there's a node whose type is constant generator and whose label is gen. And this expression, for example, means there's a connection between DS and other, and this connection connects the first pin of the output of DS to the second pin of the input port of other. Okay. Once nodes and branches of the model are constructed, the model is already constructed and it is ready for simulation. And to simulate the model, we use a simulate function. During the simulation log is constructed, and you can see that simulation is started and model is inspected before initialization and running the simulation. After the inspect stage, the model is initialized and run. If everything goes well, the simulation is terminated with success. After the simulation data can be read back from writer components. For example, we read simulation data from the writer component and we plotted the data as shown on the right. In Jusdl, signal flow approach is adopted. In signal flow approach, a model consists of connected components. We have components and connections in our model, and components process data while connections transfers data between components. In addition to the components and connections, the model has also a reference clock, and with the help of this reference clock, clock ticks are generated, and these clock ticks are passed into the components to trigger the components. Once triggered, each component reads its time, its input value from the input port, and calculates its output by solving its mathematical equation. And the calculated output value is written to the output port of the component and then transferred to the other components via connections. So during the simulation, components evolve individually. Each component reads its own time. Each component reads its own input value and solves its own mathematical equation. So components evolve individually during the simulation of the model. You can see the component types. Here we have basically three types of component types: source, sink, and system. System component can be divided into two as static system and dynamical system, and dynamical system can be divided into six, as you can see here. To represent a source, we must specify a function or relation that relates the current time t to the output part of the component. And for example, to represent a static system, we must specify a function or relation that relates the input and current time t to the output value of the component. On the other hand, you can see that we must specify two equations to construct a dynamical system. The first equation is the differential equation, and the second equation is the function relation that relates the state, input, and current time t to the output of the component. Okay, arrows here shows the input ports and output ports of the components, and the source component does not have any input port because its output does not depend on the input of the component. Similarly, a sink component does not have an output port because a sink component does not generate any data. Ports are the gates of the components. Data flows from the outside world to the component through input ports, and again data flows from the component to its outside world through output port. So we have basically two types of ports: input and output port, and each port consists of pins, and we have again two types of pins: input pins and output pins. And in addition to the input and output port, the component has two special pins: trigger and handshake pins. And these special pins are used for signal purposes between the task manager of the simulation and the component during the simulation. Okay, the processed data, data is processed by the components and transferred to the other components via connections. And the connection is actually a bunch of links. A link is built upon on Julia channels, and data flowing through the channel is also buffered and recorded as a simulation data. In order for the data to flow through the channel, some specific tasks must be constructed and bound to the channel. Before going on with those concepts, let's see an example connection. We connect component I to component J. We connect the output port of the component I to the input port of the component J with this connection. And input port and output port of the components has 3 pins each. Okay. In order for the connection to be readable and writable, some specific tasks must be constructed and bound to the connections. For example, in order for a connection to be a readable connection, a reader task must be constructed and bound to the connection so that we can read data from the connection. Similarly, in order for a connection to be a writable connection, writer task must be constructed and bound to the connection so that we can write data to the connection. If we construct both a reader task and a writer task and bind those tasks to the connection, then the connection is a readable and writable connection, and data can flow from one end of the connection to the other end of the connection, and data flows from the end corresponding to the writer task to the end that corresponds to the reader task. Okay. In JuliaCon, simulation is carried out in a couple of steps. We first start the simulation, and before running the simulation, we first inspect the model to see if the model is suitable for simulation. If the model is unsuitable for simulation, the simulation is terminated at this step. For example, the model may have algebraic loops that cannot be broken automatically, or may have unterminated connections. In any of these cases, the model is not suitable for simulation, and the simulation is halted at this stage. If the model is suitable for simulation, the next stage is the initialization stage. At this stage, the tasks corresponding to the components are launched. For example, we see an example model part consisting of the components B1, B2, and the connections L1, L2, and L3. As you can see, component B1 reads data from L1 and writes data to L2, and component B2 reads data from L2 and writes data to L3. And you can see the tasks that are launched for these components. The important point here is that we constructed a writer task and a reader task, and we bind these tasks to the connection L2, and This makes L2 a readable-writable connection, and the data now can flow from component B1 to component component B1 to component B2 through the connection L2. Okay. After the initialization step, in initialization stage, run stage comes, and in the run stage, components evolve. In evolution of components starts at the initial time of the reference clock and goes on until the final time of the reference clock. And this evolution is carried out between simulation sampling periods. And after the run stage, simulation is terminated, all the files opened and all the tasks launched in the initialization stage are closed and terminated securely. Okay, we can construct models in two different ways. In the first way, we start from scratch. We construct an empty model, and we gradually add new nodes and new branches to the model. As we add new nodes and new branches to the model, the signal flow diagram of the model is modified accordingly to keep track of the topological changes in the model as we add new nodes and new connections to the model. Okay, let's start from scratch. We construct an empty model here, and we add our first node. We use add node function for that purpose and specify the name of the model, and then construct the component, and we give a label to the component here. So we add our first node to the model. Let's keep adding our remaining nodes, and at this stage we added all our nodes. The next step is the addition of the branches of the model. For that purpose, we use a branch function and specify the name of the model. And this expression means again the same. There's a connection between gen and adder, and this connection connects the first pin of the output port of the generator to the first pin of the input port of the adder. Okay, let's keep adding our remaining branches. For example, we add the branch between adder and gain, and we add the branch between gain and writer, and we add our last branch between gain and adder at this stage. Model is ready for simulation since it's constructed. Okay, in the next way, we just describe the model. There's no modification here, we just describe the model at once. We start with a def model macro and specify the name of the model. Then between end block, we specify nodes and branches. Okay, we went through this notation before, and there's no reason to spend time here. Okay. Once a model is constructed, the next step is the simulation of the model. In this, on the left, we have a simple model consisting of just two components. We first construct the model. The next step is the simulation of the model. But before the simulation, we can configure some simulation settings. For example, we can specify the simulation directory. We can specify whether a log file should be created or whether a report file should be created. We can specify. We must actually specify the start time and final time of the simulation and steps under the simulation. With this simulation settings, the model can be simulated as shown here. And after the simulation, all the files related to the simulation is written to the simulation directory. For this example, we have three files. The first file corresponds to the writer component here, and we have a report file and we have a log file. You can see the content of the log file on the left, and you can see the content of the report file on the right. For example, you can have some information about the simulation status, and you can have some information about the components of the model that's being simulated. Okay, of course, the simulation data can be read back from writer files. For example, here we read the simulation data from the writer component, and we plot the data as shown on the right. Okay, algebraic loops may be problematic in this kind of clocked simulation environments. An algebraic loop is a closed loop that consists of feed-forward components. A component is a feed-forward component if its output depends directly on its input. So a feed-forward component must read its input first to calculate its output. Since none of the components in an algebraic loop can generate output to break the loop, simulation is got stuck in case of existence of an algebraic loop in the model. We can break these loops automatically in Jusdl, but before going on with the example, let's solve the loop equation manually. Let's say RT equals T, and if we solve the loop equation, we can find our YT equals RT over 2. Okay, let's construct the model using Jusdl and simulate it. And from the simulation log, we can see that the algebraic loop between the components 2 and 3 is detected and broken automatically, and everything went good without a hassle. And from the simulation result, we can see that yt equals rt over 2. Okay. Jusdl provides a component library. For example, users can construct sine wave generators, adders, multipliers, etc. And this component library is not strict and can be extended by the users. For example, let's say we want to extend the source components. For that purpose, we use the source macro here and go on with the keyword struct, and then specify the name of our new type. If our type is parametric type, then we specify the parameters of our type, and we make our new type as a subtype of abstract source. This is important for our new type to work properly in Jusdl environment. Then we specify the parameters of our new type, and we specify the readout function and output port of our new type with default values, as you can see here. And if you look at the field names of our new type, we can see alpha, beta, readout, and output. But we can also see some additional field names here. And these field names are added automatically via the source macro. And these additional field names are necessary for our new type to work properly in the Jusdl environment. We can see the constructors of our new type. We have two constructors, and you can see some examples to construct instances of our new type on the right. In order to see our new type working properly in Jusdl, let's construct an instance of it, and then construct required pins and ports, and connect these pins and ports to our new component, and launch the required task to trigger the component. And let's trigger the component at t equals 1, and we can take data out of the component, and this means that the component works properly in Jusdl. Okay, we just looked at the source macro, and there are other macros that help the users define their own component types, and you can see the macros, component types, super type, and other field names for each macros from this table. In the previous examples, the models has just a single algebraic loop. Jusdl also detects and breaks multiple algebraic loops. For example, we have a model that has two algebraic loops, and these are the equations that represent dynamical systems 1 and 2. Let's first construct the model and then simulate the model. And from the simulation log, we can see that both of the algebraic loops are detected automatically and broken automatically, and everything went good. And you can see the simulation result on the right. Okay, we said that Jusdl simulates models that have components that are represented by different equation types. For example, we have an example model here. In this model, we have a component that is represented by ODDS and another component that is represented by Stochastic Differential Equation. Okay, you can see the Ordinary Differential Equation corresponding to ODDS, and you can see the Stochastic Differential Equation corresponding to the STE system. Okay, let's construct this model and then simulate this model. And from the construction, you can see that the components are constructed individually. We just constructed an ODDS, we just constructed an STDS, and we connect those components together, and the model is ready for simulation, and you can see the simulation results here. So there is no need to construct a unique mathematical equation that represents the whole model. Just construct the components as they are and connect them together to simulate the model. Okay, it's possible to define plugins and integrate those plugins in Jusdl. For example, we have an example model here. Writer 3 is constructed to show that user-defined plugins is possible in Jusdl. We first define our plugin as shown here, and we construct writer 3 with this plugin as shown here. And then we simulate the model, and we read data back from the component, and from this result, we can see that it's not the time series that is written to the file of component writer 3. It's the Lyapunov exponents that's written to the component, that's written to the file of component writer 3. So the data flowing through this connection from ODDS to gain is processed online. It's processed during the simulation, and this is done with this user-defined plugin, the open-off plugin. Okay, so it's possible for the users to define their own plugins, and it's possible for the users to carry out any form of online data analysis. Okay. What are our feature plans? In our feature plans, developing a complete DSL in our feature plans, developing a complete DSL is very important, and DSL. Actually, we started to devise this DSL. For example, you can solve the macros at graph model, at nodes, at branches, etc. But this DSL is not ready for large-scale complex dynamical networks, and this DSL should be improved to effectively construct and effectively simulate large-scale complex dynamical networks. Integration of parallel computation methods at a model simulation level is also in our future plans. Actually, we use tasks to simulate models, but as you know, tasks are opened in the same Julia process, and we want to distribute the simulation workload to available cores. So integration of parallel computation methods is very important for our future plans. Okay. Developing a complete plugin manager is also in our future plans. Users can define their own plugins, but we need a complete plugin manager to securely add, remove user-defined plugins in a JuliaCon environment. From the first release of the package, the name JuliaCon is not welcomed by the Julia community, and we think to rename the package. So please specify which one from the below candidates do you think is the best for renaming JuliaCon. By the way, my favorite is System Simulation Toolkit. So for your answers, please take the survey shown. Take the survey at this link, and please specify your answers. That's all. Thank you for listening.